Okay, not many students have joined. 12, 12 students have joined already. Okay, let's not wait. We should. Okay, let me now share my computer screen. For your information, I have printed your test one because I want to mark them on the hard copies, rather than on the soft copies. It will be much easier for me to mark your test one on the hard copies, yeah. And then when I'm finished marking and grading, I will let you know your marks. But I will not return the hard copies that I have marked. I'll just let you know what marks that you get, for each question. Yeah, that's what I plan to do. Yeah. Okay, let's review what we have discussed last Wednesday. I've showed you some examples. Last week I've introduced you this concepts of triple integrals, and then I've shown you some examples of evaluations of triple integrals. Yeah. Then we look at some applications, finding the mass of a solid object. Yeah, solid object using triple integral. And then sometimes we just want to evaluate triple integrals without any view of application, just a matter of evaluation of triple integrals. Yeah. And sometimes there are several orders, dx, dy, dz. Yeah. Altogether, there are 6 possible orders, but sometimes choosing one order is sometimes easier than the others. Yeah. So sometimes we need to do some thinking, yeah, before evaluation. And then here is an example on finding volume of a solid. So a sketch is usually helpful to determine the bounds of the region of the solid under consideration. Yeah, yeah. And here is an example of finding the total charge. If the total charge, yeah, total charge. If the charge density is known, then the total charge of an object is given by this triple integral. Again, it is helpful to make a sketch. Here we have to use the combination of for, when the triple integral reduces to the double integral, then we apply the polar coordinates, the double integral in polar coordinates. Yeah. Yeah. Because the domain R here is circular. Yeah. In the another example, we look at given a solid D, we want to evaluate the given triple integral. So again, a sketch is useful to help us determine correctly the region and the bounds of the variables. Yeah, yeah. So that's what we have discussed um, last Wednesday. Any question? Do you have any question?
No, sir.
All right. So let's move on to um, evaluation of triple integrals using cylindrical coordinates. Yeah. So depending, sometimes we have object in the form in that involves cylindrical. Yeah? So it is advisable to evaluate the integral in terms of cylindrical coordinates. Yeah. After later on, maybe tomorrow, I will discuss triple integrals in spherical coordinates, where the object involved in where the solid object involves spheres. Okay, you are already familiar with Cartesian coordinates. So what is shown there? Have I started sharing? Yeah, I'm already sharing with you. Um, so you're already familiar with Cartesian coordinates, yeah, x, y, z. So x is the plus or minus distance PL, depending on which octant P is. So x, y, z can be positive or negative, yeah. And y is plus or minus distance P, the point P with M, the perpendicular distance P and M, the perpendicular distance between P and the x z plane here. While z is the perpendicular distance of P from the xy plane, or P from distance Pn here. So a point in space can be represented by x, y, z in terms of Cartesian coordinates. Okay, so you're already familiar with this, yeah, with this system. Another system which is sometimes useful in certain applications is cylindrical coordinates. Yeah. So in this here we have the same point P can be represented in terms of r, theta, and z. Yeah. Where r measure is the perpendicular distance. Yeah. R is the perpendicular distance from P to the z-axis. Yeah, represented here as capital R. And theta is the angle. Okay, if I draw a plane consisting of the point P and the z-axis, okay, here we have a plane here in green uh, that contain the point P as well as the z-axis. Then there is an angle, isn't it, between the xz plane and the plane in green here. Uh, and we denote the angle as a theta. Uh, Theta has direction, so the positive direction is shown here. Yeah, from is measured from the x-axis. The angle theta is measured from the positive x-axis. Okay, in the positive direction. So theta measures the angle between the xz plane and the plane containing point P and the z-axis. Okay, and it is measured in a positive direction. Yeah. So theta here can take values between 0 up to 2 pi, or can also take values between minus pi to pi. Yeah, from minus pi to pi. Yeah. Okay, from minus pi to pi. Yeah. So a point in space P can also be represented using this cylindrical coordinates r, theta, and z. Capital R, theta, and z. Excuse me. Sometimes the small letter r is used instead of capital R. So, because you see here on the xy plane, capital R may also be viewed as a r, a small r, right? In polar coordinate, we use r, a small r. Yeah. So we can also use small r instead of capital R in the cylindrical coordinate system. So there's of course we have relationships between the Cartesian coordinate and the cylindrical coordinate. So the relationships are shown below there. So the relationship on the left shows um, that is it using triangle trigonometry. X is r cos theta, y is r sine theta, and z is equal to z also. Yeah. And on the right is a relationship uh, how to uh, uh, how to express r theta z in terms of x y z. So if we are given a coordinate in terms of Cartesian, a point in terms of Cartesian coordinate, So the relationship on the right shows the conversion of a point in Cartesian coordinate to what? To the cylindrical coordinates. Yeah. So again, from the relationships on the left, you can derive that r is the square root of x squared plus y squared. Okay, r is the distance, right? R is the distance. So using the distance formula, it is also equal to square root of x squared plus y squared. And theta is written as tangent y over x. Yeah, but we need to be careful when applying this inverse tangent formula, because your calculator gives only values between minus pi and pi over 2. Because when we talk about inverse tangent, we restrict we want the inverse exists if the function is 1 to 1. So tangent is 1 to 1 function for between minus pi over 2 and pi over 2. Yeah. So you need to be careful. Sometimes the calculator value gives the correct value. Sometimes it gives you the wrong value. Yeah. But the value given by the calculator can also be used to determine the correct value. Yeah. I will show you some examples. Yeah. All right. So basically, tangent theta is y over x. Okay, let's see some examples of converting points in um, Cartesian to cylindrical coordinates. Mm, example. Want to write the Cartesian coordinate x, y, z equal to 2, 2, 2 square root 3, 7 as in terms of cylindrical coordinate. Yeah. So we have a point P in terms of Cartesian coordinate x, y, z. What is the point in terms of cylindrical coordinate? So that means we need to find r, theta, and z, right? Yeah. So use the previous relationship. Here we have seen this. Let's apply this relationship here. This one here. Okay. So recall this relationship. Yeah. So what is r? R is equal to square root of x squared plus y squared. So x here is 2 and y is 2 square root 3. Okay, substituting into this relationship, and then simplify. We have square root 4 plus, what is that? 4 times 3 is 12. So we have square root of 16, which is 4. Okay, r is equal to 4. What about theta? Y over x. So y here is 2 square root 3 over 2. So this is inverse tangent of square root 3. So this is a special angle. So tangent of 60 degrees is square root 3. So 60 degrees. So the answer is 60 degrees. In radian, it is pi over 3. Yeah. And z is equal to z. Remains the same. Yeah. Now, is this acceptable? Just now I inform you about we need to be careful when finding theta inverse using the inverse tangent. Is this acceptable? The question is it acceptable? Uh, so look at where the point is. Look at the point where x, y, z is. It is in the first octant, isn't it? It is in the first octant. Yeah. X, y is in the first quadrant. Okay. First quadrant. Yeah. The point is in the first octant. And xy is in the first quadrant. So pi over 3 is also in the first quadrant. Yeah. So this is the point here is in the first octant. Yeah. And then this pair of points too is in the first quadrant. Okay, on the of the xy plane. In the first quadrant of the xy plane. Yeah. So the given point here is also in the first quadrant of the xy plane also. So the answer is yes. Okay, the answer is yes. The angle is in line with the position of the point with the given point. Yeah. So then the calculator value here is acceptable if you use your calculator. Yeah. So therefore, r theta z is equal to 4 theta is pi over 3 and z is 7. This is the 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 equivalent polar coordinate, cylindrical coordinate for the Cartesian coordinate. Okay, any question? Let's look at another example.
Doctor,
Yeah.
you write the in small letter. Is it okay?
Oh yeah, yeah. As I said, sometimes we use small letter also. It is acceptable. Yeah.
Or
Okay.
which means there is no problem, right?
No, 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 no. You can
Okay,
also
okay.
use big letter. Uh, can also use small letter. I should make a note here. Um, I should make a note here. Yeah, sometimes. Oops. Let me make. Yeah, I need to comment here. Sometimes. Oops. Sometimes. The small letter R is used instead of the big capital R, yeah, for polar coordinate. Okay. Hmm. Yes. So any question? So I can also write this as R theta Z also, right? Yeah. Okay, let's look at another example. Given x, y, z equal to minus 2 square root 3 7. So we want to find r theta z, okay, for this point. So So again, recall that relationship. Oh, what did I? So again, recall this relationship. Um, hmm, what is this box doing here? Okay. So let's use this relationship once more. We replace x by -2 and y by 2 square root 3. The result is the same as before, right? Which is plus 4 plus 12 and square root of 16 equal to 4. What about in the inverse tangent? Here we have -2 2 square root 3 divided by -2, which is the inverse tangent of minus square root 3. Okay. Now, if you use your calculator, it will give you what? Minus, right? Minus 60 degrees, which is minus pi over 3 radian. Is this acceptable? The question is this acceptable? Well, look at the position of the given point. -2, 2 square root 3 lies in which quadrant? Okay, look at the point xy. -2, 2 square root 3 lies in the which quadrant of the xy plane? I'm just focusing on the xy plane here. It's in the second quadrant, right? Yeah, it's in the second quadrant. The point is in the second quadrant here. -2, 2 square root 3 is in the second quadrant, while this angle is in the fourth quadrant. It's in the fourth quadrant here. So it is not. So the angle is not in line with the position of the point. Yeah. So that means the answer here is no. However, the value given by the calculator can help us determine the right angle. So we know that the angle here is pi over 3. Okay. And therefore, the correct angle here is theta equal to 2 pi over 3. Yeah. 2 pi over 3. So this is the correct angle for theta. It is in line with the position of the given point. Okay. So the point xy here is in the second quadrant, while the angle minus 60 degrees is in the fourth quadrant. However, the calculator value can help us determine the right angle here, as shown in the diagram here. So therefore, r theta, the cylindrical coordinate for the given point is 4. Theta is 2 pi over 3, and z remains the same as given z, which is 7. Okay, any question for this example? I hope it's clear now, right? That you need to be careful when finding theta for the cylindrical coordinate here. Okay, let's see now. Now that we have a new coordinate system called the cylindrical coordinate, so how do we express a triple integral from Cartesian to cylindrical? So recall this double integral in terms of polar coordinate. Yeah, you have seen how to express a double integral from Cartesian into a double integral in terms of polar coordinate, right? Yeah. So this idea is also helpful when you want to express triple integral in cylindrical coordinates, because cylindrical coordinates have r theta, which is a polar coordinate. Yeah. Yeah. So here you see dx dy becomes r dr d theta. Yeah. So here in this diagram, r is bounded between two functions of theta, and theta is bounded by two angles here, alpha and beta. So this is the double integral in polar coordinates. Yeah. Okay. Now coming to, suppose we have an object. Yeah, a G here as shown. It looks cylindrical here, like a cylinder bounded by two surfaces, right? The upper surface is z equal to f1 xy. The lower surface is f2 xy. Yeah. And the domain x, the point xy is over this domain D in red here. Okay, so if it is cylindrical, then the domain D is circular. Yeah, circular. So using this the above idea, so if we are given a triple integral of over a solid G, okay, then Z remains the same, right? Z, first we evaluate the integral with respect to z, because z is bounded by the upper surface and the lower surface here. So let's call this inner integral as a function of xy. Okay. Once we have evaluated the innermost integral, it is in general a function of xy. So then we express this double integral into polar coordinate as shown. So then finally we replace g here as this inner integral here. All right. So this is the, the conversion formula for a triple integral from Cartesian coordinate to polar coordinate to cylindrical coordinate. Yeah. So here dv, the volume element is r dz dr d theta. Okay. R dz dr d theta. You see. So we don't have any more xy here. Yeah. Even x in the function f1, f2, we have replaced xy by r cos theta and r sin theta. That is the relationship of xy with r and theta. Okay. Mm. In this diagram on the left, it shows why the volume element is r dz d theta dz. Okay. For the cylindrical coordinate here. Okay, now let's see some examples of evaluations. Why I cannot scroll this down? Okay. Suppose a solid G is bounded above by the plane y plus z equal to 4 and bounded below by the xy plane and on its sides by the cylinder x squared plus y squared equal to 16. So we want to evaluate this double integral g, square root of x squared plus y squared dv. Okay. We have a solid G. We have a description of a solid G bounded above by the plane y plus z equal to 4 and bounded below by the xy plane and on its side by the cylinder, x squared plus y squared equal to 16. Evaluate this double integral here. So can you imagine this object G here? The shape of this object G. We have a plane. Let's try and make a sketch. Y plus z equal to 4. Y plus z equal to 4, which is what? Uh, mm,
Straight line, is it?
yeah, yz. On the yz plane, it is a line, right? It is a line. On the yz plane, it is a line. So it is a plane here containing the line. Okay. And parallel to the x-axis. Okay. Can you imagine this plane? Because the equation is independent of x, right? It is only y plus z equal to 4. So it is parallel to the x-axis. The plane is parallel to the x-axis, containing the line y plus z equal to 4. Yeah. Okay. What about the other object? It is already given to you that the object is a cylinder. This cylinder. This is a cylinder of radius 4, right? This is a cylinder of radius 4. X squared plus y squared. You see on the xy plane, it is a circle, isn't it? Some circle. Yeah. And it is a cylinder. It is independent of z. So it is a cylinder. So imagine a cylinder being we cut the cylinder using the plane here, using a plane. Imagine we have a cylinder, we slice it, using this plane here. All right, can you imagine that? Can you imagine how that object is? So the object is bounded below by the xy plane and bounded above by this. So imagine if we have a cylinder that we. It's quite challenging, right? Something like this. Yeah. Okay. So the object looks something like this. Yeah. Okay. The in red here. The object looks something like this in red here. Okay. So we want to evaluate this triple integral for this object G. The xy plane is z equal to 0, right? The equation of the xy plane is z equal to 0. Yeah. So it is easier, to evaluate. It is suitable to evaluate this triple integral using polar coordinate. It means in terms of cylindrical coordinate. Okay, so z is between the upper plane. So you can see here that z is bounded below by the xy plane, which is z equal to 0, and bounded above by this plane. So if you solve for z is equal to 4 minus y. Okay, 4 minus y there. If we try to evaluate this triple integral in terms of Cartesian coordinate, then it will have a more complicated form. It will have a more complicated form. In terms, okay, let me try express this in terms of Cartesian coordinate first. How would the triple integrals here in terms of Cartesian coordinate? Dz. Okay, we integrate first with respect to z. Z is between 4 minus y and 0. And then what about y? Okay, if you look at this, the xy plane, circular, right? On the xy plane, it is a circle. This blue region here on the xy plane, it's a circle. So the equation of the circle is x squared plus y squared. X squared plus y squared equal to, is it 4 or 2? 16. 16. X squared plus y squared equal to 16. So that means y is bounded above by the square root of 16 minus x squared and bounded below by the semicircle minus 16 minus x squared. So the inner integral is with respect to y is bounded below by minus square root of 16 minus x squared and bounded above by positive 16 minus x squared. And lastly, we integrate with respect to x. So x is between minus 4 and 4 there. So if you want to evaluate this triple integral in Cartesian coordinate, this is how it looks like. Yeah. So it looks complicated, right? Complicated. It has a complicated looking form. Mm. So let's apply cylindrical coordinate. Okay. So let's apply uh, cylindrical coordinate. So consider again the given integral, triple integral. So how is the integral now looks like? Z is between 0 and 4 minus y again. Right? Um, we have here x squared plus y squared dz. Yeah, and then um, what is it? R dr d theta, right? R dr d theta. Yeah. So we know that R is between R for this circular region. Uh, R is bounded between 0 and the radius 4, and theta, because this is a full circle, theta is bounded between 0 up to 2 pi. So R is bounded between 0 up to 4, and theta is bounded between 0 up to 2 pi. And then we need to replace xy by the relationship with the r and theta. So y is r sine theta, and the square root of x squared plus y squared is r squared, isn't it? Yeah. Dr d theta. Let me put that r in front. Okay. You see, so it has a much simpler looking form than the Cartesian triple integral in what? In Cartesian form. Yeah. Because why r squared there? Because x is r cosine theta. X is r cosine theta. Y is r sine theta. So we always have x squared plus y squared equal to r squared. Okay, the square root of r squared is r, so r times r is r squared. So this is the same as r squared. So we integrate r squared with respect to z is r squared z. Then we replace z by 0 and z equal to 4 minus r sine theta. Okay, then we have dr d theta. So first we replace z by 4 minus r sine theta. When z is 0, it's 0, so minus 0. Okay, so now it reduces to this double integral in terms of polar coordinate. So first we integrate with respect to r. So first we multiply r squared into the bracket, and then we have 4r squared minus r cubed sine theta d theta, dr d theta. Now we integrate with respect to r. So the answer is 4 over 3 cubed r cubed minus 1 over 4 r to the power of 4. R is between 0 up to 4. Okay. Now we substitute the upper limits and the lower limits of r and then take the difference. When r equal to 4, it is what? 60, it is 81, right? 4 cube is 1664. 64 times 4 is what? 256, isn't it? 256 over 3 minus. Here also we have it is 4 cube. 4 cube is 64. Sine theta d theta. Alright. Can I leave it to you to evaluate this single integral? should be no problem. I leave it to you that
Can
as an
I
exercise.
can I see up a bit?
Yeah. Yeah. Yeah.
Is it? Sorry. Oh, I integrate wrong respectively. Thanks, doctor.
Is it okay now?
Yeah. Okay.
It's okay, yeah.
Yeah.
Okay, so try to show that this single integral is equal to 512 pi over 3. Okay, I leave that to you to complete the calculation here. Okay, so in this example, it is advisable to use cylindrical coordinates rather than the Cartesian coordinates, right? Because the triple integral in Cartesian coordinates involves square roots, isn't it? Involves square roots both as the integrand as well the limits of integration. So it's a lot easier to evaluate the given triple integral using cylindrical coordinate. Because as you can see, the object involves cylinder. Yeah. If the object involves cylinder, so you should think of the cylindrical coordinate. Yeah. Again, a sketch is helpful here. Yeah. To get the idea of the bounds of x, y, z, and also r, theta, z. Any question for this example?
No, sir.
All right, so let's look at another example. This is a sample final exam question. Yeah. Yeah. Evaluate this triple integral here. With limits here -2 up to 2. The middle integral has limit minus square root of 4 minus x squared. Up here is square root 4 minus x squared. For the innermost integral has lower limit square root of x squared plus y squared. And the upper limit is equal to 2. While the integrand is x squared plus y squared. And the order given is dz dy dx. Okay, by first converting it into a cylindrical coordinate. Okay, so it is suggested here that you should use the cylindrical coordinates to evaluate this given integral here. Ada kan soalan macam ni? Dalam periksaan akhir ada. So to convert this into polar coordinate, need to make a sketch. So Z is bounded. You can see here that Z is bounded between. You can see here from the given triple integral. We know what are the bounds for x, y, z. We have x between -2 and 2. What else? Y is between the lower limit -4 minus square root 4 minus x squared, and bounded above by square root 4 minus x squared, and z is bounded below by the square root of x squared plus y squared, and bounded above by z equal to 2. Okay. You can see from the inequality for y, it is related to the circle, isn't it? If you square, you get y squared equal to 4 minus x squared, which is the circle, x squared plus y squared equal to 4. So you know the bound for y is related to the circle. What about z here? What is the shape of z equal to 2 is a plane, right? It's a plane. Z equal to square root of x squared plus y squared. Remember? What is that shape? Remember what is that shape?
A circle?
What is z equal to?
A cylindrical.
Uh,
Cylinder.
it is actually a cone, you know. You must, we have discussed this. It is a
Oh,
cone, right? It is a cone. Okay. It is a cone. Z equal to square root of x squared plus y squared. It is a cone. So it's bounded below by a cone and bounded above by the plane here. By the plane z equal to 2. Okay. So imagine a cone is slashed by the plane z equal to 2. So what is the bound for xy? That's why we have the bound is here for xy in this red shaded region here. This red shaded region, the boundary is x squared plus y squared equal to 4. Okay, it's equal to 4. The cone intersect the plane. The curve of intersection is x squared plus y squared equal to 4, which is a circle. Yeah. So the object is a cone object. It's a cone. So z is bounded. So now we know that we can apply the polar coordinate here, right? For r theta, for the cone, r is between 0 up to, for the circular region, r is between 0 up to 2. Okay, the circle is of radius 2. Yeah. And theta is 0 up to 2 pi. Okay. So if I denote this integral here as I, then I is equal to we need to replace, we have z, and x squared plus y squared is r squared, right? And dz dy dx become dz r dz dr d theta, okay? R dz dr d theta. So the innermost limit is with respect to z. So z is between square root of r squared, which is r, right? Up to 2. And r is between 0 up to 2. And theta is between 0 up to 2 pi. So this is the setup of the triple integral in terms of the cylindrical coordinate. So it is a lot easier compared to the triple integral in cylindrical coordinate. Has a much simpler form compared to the given triple integral in Cartesian coordinate. So we integrate first with respect to z. Z r cubed, right? In as the integrand. So integrate z, we get so we have r cubed. The integral of z is z squared over 2. So z is between r and 2, followed by dr d theta. So first we replace z by 2. So z squared is 4. And replace z by r. So we have 4 minus r squared dr d theta. So next we integrate this with respect to r. Now you see there is no theta in the integrand, right? There's no theta in the integrand, so I can write this as a product of two integral. Yeah. Can pull out 1/2. I can pull out 1/2, the constant 1/2 in front. The integrand here is 4r cubed minus r to the power of 5. Okay, so because the integrand is independent of theta, so we can write it as a product of two integrals, one with respect to theta, one with respect to r. So the integral with respect to theta is of course 2 pi. The integral of 4r cubed is r to the power of 4. The integral of r to the power of 5 is 1 over 6 r to the power of 6. Okay. R is between 0 up to 2. Okay, 2 here cancel out. So I leave it to you to show that the result is equal to 16 over 3 pi. 16 over 3 pi. Okay? Yeah. So here's another example of evaluation of triple integral by expressing it first into a cylindrical coordinate. Any question?
No question, sir.
Okay, if there's no question, let's look at another example. Um, Related to density, related to mass and center of gravity. Yeah. So an object fills out of suppose G is a cylindrical object. um, X squared plus y squared equal to 4, bounded above by z equal to 4 and bounded below by the xy plane. Okay, determine with density function rho x, y, z equal to 20 minus z squared. So determine first the mass and then its center of gravity. Okay. Yeah. You have discussed mass and center of gravity before, right? So let's recall those formulas. The mass center of gravity. Where did we discuss it? Hmm. I need a reading glass, you know. Okay, let me where is that topic on mass? Triple integrals applications. Oh yeah. So recall this formula, yeah. If an object, a solid object G with density function sigma here, then mass is given by this formula here. Is it this one? Have I discussed this before? No. I haven't discussed this yet, right? The formula. Uh, this one is also in Malay. The one that I have discussed with you is for the
Lamina, is it?
lamina. Remember how I introduced to you the triple integrals? Yeah, no, not this one. I introduced to you the triple integrals. How did I introduce to you the triple integrals? This one? Yeah, through this problem, isn't it? Yeah, now I remember. I introduced to you this problem of triple integrals for finding mass. Yeah, the mass is given by this triple integral formula here.
Excuse me, doctor.
Yes,
I don't know if my problem or like the screen is not clear.
not clear.
Yeah,
What about other students?
I don't know.
We see very clear.
Yes.
Okay, maybe it's from your side. Because
Okay, now all good. Thank you, doctor. Sorry for
no,
interrupting.
okay, maybe it takes time, right?
Okay,
It takes
thank you.
time. Where are you?
I'm in Malaysia actually.
Oh, Malaysia.
Yeah.
Okay, so sometimes yeah, it takes time
Okay, thank you. Sorry
for
for interrupting.
through internet. So we want to apply this formula here to find the mass, right? Mass. So let's do the part one first. So the mass of the object is given by this formula, rho x, y, z, dv. Now the object is cylindrical, so that suggests using the cylindrical coordinate. That suggests using the cylindrical coordinate. Yeah, it is bounded below by the xy plane and bounded above by the plane z equal to 4. Yeah, this the plane above is z equal to 4, and the cylinder is x squared plus y squared equal to 4. Okay, so that suggests using cylindrical coordinate to compute the mass. Yeah. So first we replace rho by 20 minus z squared r dz dr d theta. Okay, the volume element in terms of cylindrical coordinate is r dz dr d theta. So z is bounded above and below by just numbers here, and r is this r theta is in this green shaded region, circular, isn't it, of radius. Um, what is the radius? Excuse me. This is 2, right? 2. Yeah, so r is between 0 up to 2, and theta, this is a complete circle, so theta is from 0 up to 2 pi. Yes. So first we integrate with respect to z. Yeah. Integrate, we have r. Integrate with respect to z is 20z minus z cubed over 3. This is to be evaluated from z equal to 0 up to 4 dr d theta. Okay, first we replace 0 up to 2. First we replace z by 4. So what do we get? We have 80 minus 4 cubed is 64 over 3. It's just a number. Okay, so 80 minus 64 over 3 is what? 240 minus 64. What is 240 minus 64? Yes. What is 240 minus 64?
176.
176, right? 240 minus 64. Yeah, 176 over 3. So this is 176 over 3. Huh? 176 over 3. And then again, we have this integral. The integrand is independent of theta. So we can write this as a product of two integral. The RdR. Okay? Yeah. So I leave it to you to show that this integral is equal to um, what? 704 pi over 3. Yeah, 704 pi over 3. Yeah. So that is the mass. The mass. Yeah. What about the center of gravity? I have discussed with you the center of gravity for lamina, right? So the center of gravity for I'm sorry, this is in Malay. Um, is given by this formula here. Yeah, it's given by this formula: x bar, y bar, z bar. Yeah, let me take a snapshot of this one. To answer part 2, we need to use this formula. Okay, this is the formula for center gravity of an object. So all the coordinates are divided by m, right? As m in the numerator, which we have calculated in the first part. It remains to find all these numerator parts. Yeah, in the formula. Okay, it is related to moment. It's all related to moment. Okay, these are called moments. Yeah. So where? Yeah, with the given moments here. Okay, it seems that we have three triple integrals to evaluate here, isn't it? But actually, both of them is zero. One is non-zero. Where do you expect the center of gravity lies? Where? Where do you expect the center of gravity here lies?
On the z-axis.
Yeah, z-axis. Due to symmetry, right? Due
Yeah.
to symmetry, and also look at this density function here. It only depends on z. Yeah. So the density function also depends on z, and the cylinder and is symmetrical. Yeah. So we expect the center of gravity lies on the z-axis. Yeah. Okay. So we expect the center of gravity lies on the z-axis. Why? Since rho is given only in terms of z, and G is a cylinder. Cylinder. Okay, so we expect, therefore, we expect x bar is 0, y bar is 0, and z bar not equal to 0. So it's enough to calculate z bar only. Okay, enough to calculate z bar only. So z bar is mxy, the moment mxy divided by m. And the moment mxy is given here in the third equation here. Yeah, so it's so it is enough to calculate only m, the moment mxy. Here the density function is sigma. So which is rho here, rho. 20 minus z squared dv. Okay, dv. So now we evaluate this using a triple. Using what? Using cylindrical coordinate. Yeah, in terms of cylindrical coordinate. So we have z times 20 minus z squared r dz dr d theta. Z is between what? Z is between 0 and 4, right? Z is between the xy plane and the above by z equal to 4. And r is bounded between 0 up to 2, right? The cylinder has radius 2. And it is a full cylinder, so theta is between 0 up to 2 pi. You see all the limits are numbers. Yeah. And the integrand can be viewed as a product of functions of a z and function of r and function of theta. So I can write this as a product of two integrals, three integrals. Dz. Okay, that is dz. Yeah. So should be no problem, okay, for you to evaluate this integral. So I leave it to you to show that it is equal to 704 pi over 3. 70, is it so?
Haven't yet, because we just got mxy, the z
Oh,
coordinate.
yeah. That's right. We need to do something else, right? Yeah. This is 2 pi. The first integral is 2 pi. The second integral is r squared over 2. R squared over 2. 4 over 2 is 2. What about this third one? This is 20 z minus z cube. So the integral of that is 10 z squared minus 1 over 4 z cube. Z is between 0 up to 4. So this is 1/2 r squared. This is 4 pi times what? And z equal to 4. First term is 160 The second term is 4 cubed over 4, which is 4 squared, which is 16. 16. What is 160 minus 16? what is 60 minus 16? 44, right? 144. Yeah. And multiply that by 4. 4 squared is 16. 24. 4
Doctor,
squared is 6. Yeah.
the z power of 3 is not power of 3, is power of 4, right?
Oh, yeah, you're right. Betul lah. Yeah, you are right. Thank you.
Okay.
So 4 to the power 4 divided by 4 is 4 cubed. 4 cubed is 64, right? 64. So what's that? 160 minus 64 is
96.
196.
96 only.
Oh, no, sorry. Yeah, 96. And what is 4 times 96? 4 times 6 is 36. 36.
384.
4 times 6. Oh, sorry. 4 times 6 is 24. Yeah. 4 times 24. 4 times 9 is 36, right? 36 plus 2 is 38. Okay. So that is the moment. Uh, with respect to the
XY.
z-axis. Yeah, xy. Okay. This moment is actually with respect to the about the z-axis. Yeah. This is the moment about. This is one is about x-axis. The second equation is for moment about the y-axis, and the third moment is about the z-axis. Yeah, about the z-axis. Okay, now we can calculate z bar. Z bar is the moment whereas xy divided by m. So mxy is 384 over pi, and previously we have calculated mass as what? 704 pi over 3. Okay, can be shown that this reduces to 18 over 11. Pi cancel out. So therefore, the center of gravity is located at this point here. 18 with z coordinate on the z axis with the z coordinate 18 over 11. Any question for this example?
No, doctor.
Okay. Just now we say that, so we sometimes, you have given such question, in let's say final exam also. So sometimes this observation is important, to save you a lot of calculations. With this observation, knowledge of symmetry, you can immediately conclude x bar equal to 0, y bar equal to 0. If you calculate this integral here, you will get 0. Okay. If I have tried calculating the first moment and the second moment, it is equal to 0. Even by calculation, if you evaluate this triple integral here for the first moment, second moment, it is I have already done the calculations. It is both equal to 0. Okay. Yeah, but sometimes the values can be determined also by inspection. Yeah. Any question? So
far so good.
far
So
so
far, so
good.
good, Doctor.
Okay. Uh, so that is all that I have prepared for our class today. Tomorrow, okay, I will talk about the spherical coordinate. Yeah, if you look at the weekly schedule, we are here in week number 8. So there's one topic I want to discuss: triple integral in spherical coordinates. Yeah, and spherical coordinates. So I think I will discuss this tomorrow with you. We have another class. Yeah, and then we also look at some applications of that. So I think we are not behind schedule here. We are on time. Yeah. So next week is a mid-semester break. Following the mid-semester break, we will start with a new topic called vector value functions. Let's talk about vector calculus. Okay, all the topics after semester break is related to vector calculus. You'll see um, this vector integrals called line integrals, then surface integrals here. So these are all involving Gauss divergence theorems involve triple integrals. Stokes theorem involves double integrals. Yeah. So all that we have learned before will also be required in this topic on vector calculus. Yeah. All right. There's no further question. Then let me just show you the class attendance for today. Where is it? Okay. Check. Internet is a little bit slow here. Okay, there you are. So please scan the QR code and you may leave the class if you have no questions. So I'll see you tomorrow, 11 a.m. inshallah.
Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank you.